So this is a quick-ish, but probably not that quick rundown of the GCSE Edexcel astronomy topic. It's pretty similar for all exam boards, but this is specifically for Edexcel if you are working out which topic you should be looking at. So there's 5 main sections we're going to look at. The solar system, gravity and orbits, redshift and the Big Bang Theory, stellar evolution, and then methods of observing the universe, if I can say that properly. So if you want to skip ahead to one of those parts, feel free to. Otherwise, I will get started with the solar system. So the solar system is the sun and all of the objects that orbit around the sun. It's a type of star system, and the sun is just a star. Okay, so there is only one star in our solar system, and it is the sun. It is not a particularly big star, it just looks big because it's the closest to us. So after we get the sun, we start with the 4 terrestrial planets. So the 4 planets in order are Mercury, Venus, Earth, and Mars. Now these are what we call the terrestrial planets. And we call them that because they're quite small, they're rocky, they have a solid surface. We think that for life to exist, it's probably going to have to be on a terrestrial planet because then people can stand up. So that's the terrestrial planets. Make sure you know that there's Mercury and then Mars at this end. I haven't written them down. After Mars, we get something called here the asteroid belt, which doesn't look like I've drawn it. But it's a ring that goes all the way around the solar system of asteroids. I think Ceres is in there. I'm not completely sure. There's some dwarf planets in there. There's some big asteroids, some small asteroids. It's not particularly dense, but it's definitely more dense in terms of asteroids than anywhere else in this part of the solar system, at least. After that, we get to the gas giants. So we then have 4 more planets. We have Jupiter, we have Saturn. Oh, I managed to draw the ring through Saturn there, apologies. We have Uranus, and we have Neptune. It's really important for me to say that this is not to scale. Okay, Jupiter is the biggest planet, followed by Saturn. Mercury is the smallest planet, but I've not drawn them to scale at all. These are definitely bigger than these because these are the gas giants. I shall write that down. And the gas giants are called that because they are made of gas. We don't actually know if they've got a solid centre, or we didn't 10 years ago when I did my course in planetary science at university. But they're much, much bigger. They're made of gases which are either frozen or liquefied or just gas. The famous things to know about them are Saturn have got its rings around it and it would float. Uranus actually has its rings vertically, as you can see it. It spins on a different axis to every other planet. Then we have, outside of that, another belt. And this belt is called the Kuiper belt. And within the Kuiper belt, we do actually have the planet Pluto, which is a dwarf planet. It's not a normal planet. It's not classified as a normal planet because it has not cleared its orbit. Every other planet, as it goes around the Earth, so not the Earth, the Sun, that will come on to that in a moment, as it goes around the Sun, there's nothing in its way. They've cleared their orbits. Pluto, it's surrounded by other asteroids and other dwarf planets in the Kuiper belt, which is why it's not a planet. It's not because it's too small. It's about the same size as Mercury. So, you need to know about how ideas about the solar system have changed over time. We now know the solar system looks like this because of technology. But back in the past, before, let's say approximately 1500 or so, when ideas were definitely starting to change, we thought that the solar system was geocentric. That means that the Earth is at the centre. And we thought the Earth is at the centre of the universe. And that everything evolved around it, or orbited it. Now, it's kind of understandable why people thought this, because if you look at the sun and the moon over the day, we can see that they go up in the sky and back down in the sky. They seem to rise and set. It gives the idea that maybe they're going around the Earth. The same with the stars. If you look at the stars over the course of a night, they will spin around on an axis. The only exception is the planets. If you can actually see some of the other planets, they look like stars but a bit more fuzzy. And they didn't just do a path like this. They do a weird little path that looks like this. called retrograde motion. So they seemed a bit strange. They were wandering stars, and that's why they're called planets, because planetas means wanderer in Greek. But this is a problem. Everything else seemed to fit, but this wandering planet thing didn't seem to. So some people started to think that maybe the solar system, the Earth was not the centre of the solar system and the universe, and actually was that the sun was at the centre. Now, I'm not going to write universe, I'm going to write sun at centre of solar system, because we now know that the sun is not at the centre of the universe, it's in an outer edge somewhere, but the idea that we're not the centre on the Earth, that something else is. Now, the reason that this came to be believed is because we had better technology. So, for example, telescopes were invented, and Galileo was able to use a telescope to find the moons of Jupiter. And the moons of Jupiter are quite important because they proved that there was another body with things orbiting around it. So if moons orbited around Jupiter, that meant that not everything went around the Earth. So maybe the Earth went around the sun. And as we increased our technology, we had more and more evidence. And by about the 1700s, this was generally being believed that the sun is at the centre of the universe. Not the universe, the solar system. Before that, it was heretical to say it, and you could actually be put to death by the church. So, we now know what the solar system looks like. We do, however, need to know about the different orbits in the solar system. So here I've got the sun. Planets orbit the sun. Now, orbit just means go around. So the planets, I'm going to draw a planet here. They will go around the sun in a roughly circular orbit. They are a little bit elliptical. Ellipses are just ovals. A circle is an example of an ellipse, by the way, but they're roughly circular. Then we have moons. Now, moons are just natural satellites of planets. That means that they are objects that aren't man-made that orbit another planet. So a moon, any moon, including our moon, will orbit a planet in, once again, a roughly circular orbit. So you've got a planet orbiting the sun in a roughly circular orbit, and then a moon orbits a planet in a roughly circular orbit. There's one more orbit we need to know about, and that is the orbit of comets. Now, comets are not asteroids. Asteroids are lumps of rock. Comets are collections of frozen rock and gases that are held together by the frozen gases, and things like frozen nitrogen, etc. And comets have got very, very elliptical orbits. So comets have an orbit that looks like this. We say that they're highly elliptical. And we say that because, well, they are highly elliptical. That happens because the comets swoosh around. When they're near the sun, they're very fast. And then they slow down as they get further away. As they get further away, they get very cold, and therefore they freeze. And then as they swoosh and get close to the sun, they start to melt, and you see the melted tail behind them. And that's what you see when you see a comet. You see like a tail behind it. And that tail is those melting gases. So that's the basics about the solar system. We need to know a little bit more here about orbits and gravity. And personally, when I teach this, I put this section into a different topic. I teach this within forces because I think it fits better there with the way that I teach it. But it's technically in the space section. So for things to orbit, they need to have gravity, and we need to know about something called gravitational field strength. Now, gravitational field strength tells us what the weight of 1 kilogram, a mass of 1 kilogram, is on a planet. You might remember the equation, W equals mg, weight equals mass times gravitational field strength. Now on Earth, gravitational field strength is 10 newtons per kilogram. Each kilogram weighs 10 newtons. And sometimes we write this as 10 meters per second squared, which is the acceleration due to gravity. It's the same number. On the moon, that value is 1.6 newtons per kilogram. So if you go to the moon, you have the same mass, but you will weigh substantially less, about 7 times less. On Jupiter, that value is much higher. It's 26 newtons per kilogram. And you can probably work out what factor is helping this. Now you might think straight away, oh well, it's the size. The moon is smaller than the Earth and Jupiter's bigger, therefore it's size that depends on gravitational field strength. To an extent it is, but what do we mean by size? So to know that, we need to think about something called surface gravity. And surface gravity is simply what is gravitational field strength at the surface of the planet, and that's what I've told you here. Now, surface gravity depends on mass and radius. Now, when we're thinking about the size of these planets, the reason that Jupiter has got a bigger gravitational field strength than the Earth isn't just because it's bigger, it's because it has a higher mass. So the more mass something has, the more gravity it has. So for a given radius, for a given size of planet, if I had two planets that were identical sizes, but one was heavier than the other, had more mass than the other, then the gravity of that more massive planet would be higher. So as mass increases, gravitational field strength or surface gravity increases. The second factor that surface gravity depends on is radius. If I had two planets of the same mass, but one was much bigger than the other, actually the smaller planet would have a higher gravitational field strength because it would be more dense, and the bigger planet would be less dense. Therefore, we can say that as radius increases for a given mass, g actually decreases. Really, we can say that surface gravity depends on density. The higher the density, the higher the gravitational field strength. So, knowing that, we need to know a little bit about orbits. Now, to think about what an orbit is, we can use Newton's thought experiment. So Newton said, imagine that you had a cannon and you had it on a hill and you fired it. You'd see this happen. It would fall to the earth like so. If you fired it a little bit faster, with a higher speed, you put more gunpowder there, you would find that maybe this happened. And if you fired it at a specific speed, faster again, you might find that this happened. It would keep falling, but it would never actually hit the earth. And in that circumstance, that's what an orbit is. An orbit is when an object is basically always falling to earth, but always just missing. Now, orbiting planets or orbiting objects around a planet are examples of circular motion. So here I've got my satellite. I'm going to say that it's travelling in this direction. Its velocity is in this direction. But when the satellite was here, its velocity would be in this direction. So we can see that although the speed might be constant, which it is, the direction of the speed of the satellite is changing, which therefore means the velocity is changing, because velocity is the speed in a given direction. And a change in velocity means that the satellite is accelerating. And for acceleration to happen, we must have a force needed. And this is a centripetal force, which is in the forces topic. And that force will always act towards the centre of the circle at right angles to the velocity. And the centripetal force for an orbit is gravity. Now, if I wanted my satellite to move into an outer orbit, so move to a further away orbit, like so, to do that I would have to change its speed. And for a larger radius of orbit, I need to decrease the velocity. It needs to go slower. Because there's less gravity, or the gravitational field strength is lower at this point because it's further away from the object. If you think about spinning around a ball on a string around your head, or a bucket of water, you might have tried that before where it doesn't fall. If you have it on a small circle, you have to spin it much faster to keep it going and not hit you or fall on you than if you have it going in a big circle. So the larger the radius of orbit, the slower it needs to go. So if you want a satellite to move from this orbit to this orbit, you just slow it down and it will gradually do it itself. Now there are 3 or 4 orbits that we need to know about, standard orbits, around the Earth. And the first 2 are the most common. Now the first is what we call a geostationary orbit. And a geostationary orbit goes around the equator of the Earth, so geostationary. It's around the equator of the Earth. Its period is 1 day. And it stays over the same spot on Earth all the time. So a geostationary orbit the satellite basically tracks around the same point all of the time as it goes around the Earth, and as the Earth is spinning, remember. So that's why it takes a day, and it needs to be over the equator. Now these are used for things like satellite TV and some communications. So for example, satellite TV, you might have noticed that all the satellites point the same way. If you look at a block of flats, they're all pointing in one direction. That's because they're all pointing at the satellite. And if that satellite was moving around in the sky relative to the flats, then it wouldn't be particularly helpful because they wouldn't be able to get their satellite TV signal. So geostationary orbits over the equator have a period of 1 day, and it stays over the same spot. Then we also have polar orbits. Now, these don't stay over the same spot, as you can see. They don't have a period of 1 day, and that means they cover the whole of the Earth, essentially. Their coverage is across the whole of the Earth. This means they're used mainly for some communications or for, I'm going to say used for photographing / mapping the Earth. So you might have heard of Google Earth, which was a satellite that took photos of the entirety of the Earth. Geostationary couldn't do that because it couldn't take photographs of where it's stationed over. Whereas a polar orbit, because the Earth's orbiting this way and the polar orbit's doing this, it will cover all of the Earth. It also means that it can be used for weather, for world weather. Geostationary could be used for local weather. It also means that it's often used for spy satellites. So yeah, they're the two main ones to know about. There's two more that we can know about, and they have highly original names. One is the, highly elliptical orbit, kind of like a comet. That's used for communications near the poles, where it's difficult for the other satellites. For example, the geostationary satellite's quite hard there. And then there's also a low Earth orbit, which looks a bit like a geostationary one, but smaller. It doesn't go at the same speed as geostationary. This is the only place where, the geostationary orbit is the only place where it would take 1 day to have a period to go around the Earth. The low Earth orbit is kind of the easiest orbit that we can get things into. It's the cheapest because you need less rocket fuel to get there. So it's the lowest one. So that's gravity in orbits, which is quite a separate section to everything else, which I'm more comfortable with. So we move on to redshift and the Big Bang Theory. Now, redshift and the Big Bang Theory is what we call cosmology. And before we start, we have to know about the EM spectrum and the visible spectrum. And we need to know that if you look at different colours of light, they have longer and shorter wavelengths. The longest wavelengths are red, the shortest wavelengths are violet, and we go from red, orange, yellow, green, blue, indigo, violet, and as we go this way we decrease the wavelength. That's going to be important. So when a galaxy emits light and it comes towards the Earth, that light is emitted and it travels towards Earth like so. And I've drawn here 3 full waves. If the galaxy is moving away from us, it can't just add in a few more waves as it travels away from us. We can't create light, that would be creating energy. So the 3 waves, obviously in real life it's like millions and billions of waves, but for ease here, the 3 waves have to stretch out to be able to reach the Earth, like so. This is called redshift. Now why? Because the wavelength has increased. If you look at the wavelength of these waves compared to these waves, this has got a higher wavelength. So we've increased the wavelength. So if this light was originally yellow light, I've stretched it and it's gone maybe orange. It's gone towards the red end of the spectrum, which is why it's called redshift. Orange light might go red. Blue light might go green. It doesn't mean the light has gone red. It just means it's shifted towards this end of the spectrum. Red light can be redshifted. It just shifts carrying on this way to infrared and then to microwaves, and we'll come on to that in a moment. If the galaxy is moving, so this is the galaxy moving away, if the galaxy is moving towards us, those 3 waves have to be squashed, 1, 2, 3, into a smaller space. So we decrease the wavelength and we shift the colour of the light this way. Now you might think that's called violet shift, not quite, we call it blue shift because it's shifted towards the blue end of the spectrum. So if an object's moving away from us, it'll be red shifted, and if it's moving towards us, it will be blue shifted. That's really useful because we can look at all the different galaxies in the universe, of which there are thousands, and we can see if they're red shifted or blue shifted. And what we actually see is that like 99% of galaxies are red shifted. Now think about what that means. That means that 99% of galaxies are moving away from us. Only a few are moving towards us. One example is Andromeda, our neighbour. So if 99% of galaxies are moving away from us, that comes up with a really exciting conclusion. And that's the idea that the universe is expanding. If everything is moving away from everything else, the universe is getting bigger. And we often think about this. Imagine that I've got a balloon and I draw dots on it. And then I blow that balloon up, and those dots will have all moved further away from every other dot. The universe is expanding. That's quite a common model. Now this was discovered by somebody called Edwin Hubble, and he carried on and he went to look at this little graph here. So what we find is Hubble decided to measure the redshift and use that to work out the distance and velocity of the galaxy. So he was looking at these distant galaxies and he worked out how far away they were and also how quickly they were moving away from us, their recession velocity. And he plotted a graph and he plotted a line of best fit. And the line of best fit was like this, it was a straight line. So Hubble found that the distance to the galaxy is proportional to the recession velocity, how quickly it's moving away from us. So the further away a galaxy is, the more quickly it's moving away from us. And this leads to the idea that yes, the universe is expanding, and that expansion is speeding up. Which was a big deal. This is in the 1920s he was finding this out, and we'd never known that before. Now if we think about every galaxy moving away from every other galaxy, think back in time. If all the galaxies are moving away from each other, then that means that in the past they must have been closer together. And if we keep going back, they must have been so close together they were all at one point. And this is what led to the Big Bang Theory. So Hubble didn't come up with the Big Bang Theory, but his findings helped with it. And the Big Bang Theory is this. In the distant past, the universe was hot and dense. Since then, it has expanded, cooling down, and becoming less dense. It doesn't mention the word explosion. This is my biggest bugbear. As far as I'm aware, the Big Bang Theory is not an explosion because you can't explode it, there's nothing there. It wasn't a Big Bang, there was no sound because there wasn't anything for the sound to travel through at that point. That's just a way that they used to describe it. As far as I know, a scientist was asked on the radio to kind of sum up his theory. He said, oh, it's like a Big Bang and it stuck. It doesn't say that there is a God or there is no God. It doesn't actually tell us about the very start of the universe. It actually tells us about how the universe has evolved since just after its start. So the Big Bang Theory, the main points out of that we need to know is that we've got an expanding universe that had a start, although we're not really sure how that start started. And one of the things they say is that no new matter has been created since the start. Therefore, as it expands, it's getting less dense. So its density is decreasing. Now, when I was at university, I only learnt about the Big Bang Theory because we think it's right, but not everyone did. Back in the 1950s, there was another theory that was pretty much as popular, and that was the steady state theory. And the steady state theory has some similarities and differences with the Big Bang Theory. One similarity is that it says that the universe is expanding. And it says that because these were both come up with after Hubble had worked out that the universe was expanding. So they both have some evidence of redshift. So as we knew the universe was expanding, we had to put that into the theory. And the evidence for that is redshift. However, the steady state theory says the universe has always existed. It didn't have a start, it's always been around. And it says that new matter is continually being created, which means that the density is constant. So this is quite different, okay? So we had evidence that the universe is expanding, so we didn't know which one of these was correct. And there was evidence that supported one more than the other. And then eventually what happened is something called the cosmic microwave background was discovered. The CMB, the cosmic microwave background. And I've written that on this side here because the cosmic microwave background was discovered by accident in the 1960s. It had been theorised and then it was discovered after that. And it supports the Big Bang Theory and only the Big Bang Theory. And this was the kind of the blow to steady state. The cosmic microwave background cannot exist in steady state theory, but it can exist for the Big Bang Theory, which is why we now believe this one to be correct. Now, the cosmic microwave background, when you think back to the Big Bang when there was this high energy event at the start, and at the start it gave off lots and lots of energy in the form of gamma rays and UV and microwaves, so on this end of the spectrum. And that all happened in a very, very small space. And since then, the universe has expanded, and that energy has been stretched out. It's been redshifted. So it's gone from gamma rays and UV, gone through visible light, gone through red to infrared to microwaves. So this is it's often called the afterglow of the Big Bang. And it's a background, it's all across the sky, it's microwaves that are all across the sky from this very, very high energy event at the start of the universe. So high energy radiation has been redshifted. And it suggests that the universe had a start, which is why it is evidence for the Big Bang Theory. It's the hardest bit of astronomy, I think, in your GCSE, because we can't explain it all that well, because you need to know a bit more about other bits of physics to be able to explain it more than that. So that's cosmology. That's how we look at the universe and its evolution. We now need to think about the evolution of not the universe, but of stars, stellar evolution. And the whole of stellar evolution is a battle. It's a battle between two forces in stars. One, the force of gravity, which is pulling stars in. And the gravity of a star depends on its mass. The more massive it is, the more gravity it has. Versus the force of pressure, or thermal pressure, which is pushing the star outwards. And that pressure comes from the fusion going on inside the star, creating heat, and that heat is pushing the star out. Now, this is a tug of war between gravity and pressure. If gravity is bigger than pressure, then the star will shrink. If pressure is bigger than gravity, the star will expand. And if gravity is equal to pressure, the star stays the same size. So all of stellar evolution is a tug of war between these two forces. Now, a star is made in a nebula, which is a cloud of gas and dust. And what happens is that by chance, one of these places will be more clumpy than the rest. So just be a bit that's more dense than the rest. And the more dense bit will have more gravity, and therefore it starts to drag in the dust from around it. What we say is that the nebula collapses under its own gravity. And it's like a snowball effect. So this clump gets clumpier and clumpier and clumpier, and eventually we get the start, terrible drawing there, of a star. So this clump has got so dense, and as it gets dense, the temperature increases and the pressure increases and the density increases, and we get to a protostar. So at this point in time, gravity is definitely beating pressure. Gravity is bigger than pressure, it's pulling it together. We get to a protostar where it increases in temperature and in pressure and in density until fusion of hydrogen to helium begins. When the fusion of hydrogen to helium begins, that's when it becomes a main sequence star. So a star is a body that fuses elements to power it, and when hydrogen fuses to helium, that is a main sequence star. But there are two paths that this star can go on. Firstly, if it's a sun-like or medium-sized star, so our sun is a slightly smaller than average star, it will follow one path. Or if it is a massive star, or something called a giant star, it will follow a slightly different path. Same kind of pattern, different names for things. So we start off, I'm going to look at sun-like stars with the main sequence. The main sequence is the longest and most stable part of a star's life. It's when hydrogen is being fused into helium, and during this time gravity is equal to pressure, therefore the star stays at the same size. This for a sun-like star is approximately 10 billion years. But eventually the star will run out of hydrogen and won't have enough hydrogen to fuse into helium. So what will happen is that fusion will stop when it gets from hydrogen to when it runs out of hydrogen. When fusion stops, that means the pressure is going to decrease because there's not as much heat, and gravity will cause the core of the star to contract. As the star contracts, it actually gets hotter, and as it gets hotter, that means that now helium can start to fuse to other elements, so we start to get a new energy source. And when this happens, the star becomes slightly larger. I've not got the right colours here at all. A red giant. And a red giant is where we fuse helium and other elements. In the core of the star, as I said before, to start with, gravity is bigger than pressure, which causes it to collapse. But on the outside, pressure is bigger than gravity, and that causes the outer layers of the red giant to puff up and also to cool down, which is why they become red. Eventually, it runs out of all the elements it can fuse, and that's kind of the end of the journey for the red giant. So there's two things that happen then. We get a planetary nebula, which is the outer layers. I should write that down, planetary nebula. The outer layers of the red giant float away, and that leaves behind a white dwarf, which is very small, very hot, very bright, but eventually it cools down over billions of years and kind of fades away. This whole process will take about 12 billion years or so. So a big portion of it's on the main sequence. Now, a massive star does a very similar set of things, just a bit more dramatically. So massive stars are more dramatic. I like to say they live fast and die young, like rock stars. So we start with a main sequence, but it's a massive main sequence star. Once again, helium fuses to hydrogen. Gravity is equal to pressure. That's the same for both. But this time it's only approximately, let's say, 1 billion years or so. It burns through its fuel much faster because it's so much bigger. It's like if you've got a tiny car. I've got a little Panda. One tank of petrol lasts me forever. It's a small tank, but the car doesn't take a lot of petrol. But if I had a sports car, like maybe a Porsche, the petrol tank would be bigger, but I'd also have to fill it up more often because the engine would take more of that petrol. Same thing happens, it runs out of hydrogen, gravity gets bigger because, that's the wrong way around, isn't it? Yeah, sorry, I'm just going to change that. Gravity is bigger than pressure because fusion stops, the core collapses, but then heats up as it collapses and therefore starts to fuse higher elements. The outside puffs up because the pressure is bigger than gravity, and we get a super red giant. So the same idea is happening again. Super red giants can fuse more elements, but when they stop fusing, it's a bit more dramatic. So when the red giants stop fusing, the outer layers just puffed away, they floated away, there we are. When the super red giant runs out, we get a really great artist's impression here, a supernova, which is the biggest explosions that you'll see in the universe. Supernova means big new. The Romans called them supernova because often you would see, not often, quite rare, you'd see a big new star because these supernovas are super surprisingly bright and massive. They last a couple of days, which in the grand scheme of the universe is a pretty long time. It's a pretty short time, considering how many billions of years the universe goes on for. And some of them are so bright. There was one in the 15th century, apparently, that was so bright that the sky didn't go dark for like 6 days because it was brighter than the sun. And it leaves behind, just like the planetary nebula left behind a white dwarf, the supernova will leave behind the core, but that core will be one of two things. It will either be a neutron star or a black hole. So a neutron star is if it's a smaller massive star, and a black hole is if it's a massive, massive star. A neutron star is actually made of neutrons, and a black hole is what we call a singularity. It's so dense and so powerful that even light can't escape it. So it's when the core has been packed into a tiny, tiny, tiny space, it becomes so dense that gravity is so strong. So gravity is definitely bigger than pressure at this one here, that it is sucking in everything around it, even light. So you need to have a kind of appreciation of this flow chart, really. You need to know the stages for high mass and low mass stars, and you need to know a little bit about the idea of gravity and pressure throughout. A lot of the content I've told you about the fusion is probably slightly over the top for what you need to know, but it helps me to understand it. And on my very brief, which is not brief because we're now over half an hour, look at astronomy, we've got one more topic, and that is methods of observing the universe over time. So we start off until the 1500s. We start off with naked eye astronomy. All we could do was observe what we could see with our eyes. But then in the 1500s, we start to get telescopes. So Galileo famously made the first, well, not the first, but famously made one of the early telescopes. And he made his with glass lenses. And as I said before, he discovered the moons of Jupiter. And in the 1600s, Newton, good old Mr. Isaac Newton, improved them by using mirrors. Mirrors are better for telescopes because you make them bigger and you can make them more perfect than you can make a glass lens. It's really hard to make a glass lens, especially if you haven't got machines like you didn't then. So we started to get better ideas of what's going on in the universe. This is why we started to think about maybe the solar system isn't geocentric, it's actually heliocentric. Now, our telescopes have improved over time. So the biggest step was going from no telescope to telescopes, but then telescopes got bigger. And that's good because a bigger telescope can collect more light, which means more detailed images of fainter or further stars. So the stars can be further away or fainter, and we can see them because the telescope is bigger. And we can make telescopes massive now, like meters and meters across. The fact we have mirrors is really helpful for that. And there's three kind of evolutions that's gone on since then. So firstly, we can now put telescopes, there's my hair, let's try and get rid of that, telescopes up mountains. Now this has got a couple of advantages. It moves them away from light pollution. And light pollution is annoying nowadays because if you live in a city, you don't really see many stars because it's always too bright to see them. If you go out to the countryside and look at the sky at night, you can see so many more stars. So the telescope up a mountain moves away from light pollution, but you could do that by just going into the countryside. The big thing is that it reduces the amount of atmosphere between the telescope and the stars, which means you have less twinkling, or we say atmospheric distortion. Sorry, my handwriting is pretty terrible right now. So stars don't actually twinkle. The only reason they seem to twinkle is because as they come through the atmosphere makes them, distorts the light and makes them look like they're twinkling. If we can put a telescope up a mountain, we're getting away from a lot of that, and therefore we're going to get clearer images. Mountains are expensive to build up, but they are much less expensive to build up than this example here, which is a space telescope. I've only got one so far as I know, and that is the Hubble. So space telescopes are very expensive and hard to repair / make. However, they have a massive advantage. There is no atmosphere, therefore no distortion that we would get here. People like to say that, oh, well, there's no light pollution. True. But that isn't why I'm putting a telescope in space. If I want no light pollution, I'll go to a countryside, I'll go to a mountain, which is much cheaper and easier. It's not the advantage of putting it in space. The advantage of putting it in space is that there's no atmosphere, so there's no atmospheric distortion. It's not because it's closer to the stars. In the grand scheme of things, 100 kilometres is not a big deal. This is the main reason. The other reason is that we can, it can see all EM radiations. So some types of EM radiation, some infrared, some gamma rays, some UV, are absorbed by the atmosphere, whereas if we're outside the atmosphere, they can't be absorbed. So you can have telescopes that don't just see visible light, they see other things, and that tells us lots of extra information. So the two main advantages: no atmospheric distortion because it's outside the atmosphere, and it can see all types of EM radiation. That being said, telescopes aren't all about light, as I've already mentioned. Some telescopes are radio telescopes. And this is kind of to represent other EM radiations, because we can learn a lot about the universe by not just looking at the light that that stars give out, but also the other types of EM radiation. We can look at how those stars have evolved, what types of energy they're giving out, what elements they're made of, things like that. So over time, our methods of observing the universe have gone from nothing to telescopes with glass lenses, and then to mirrors, to bigger telescopes, and then to moving those telescopes to mountains or other areas to improve their visibility, and then even into space, and by diversifying our telescopes to not just see light but to see other types of EM radiation as well. So that is space in 40 minutes, which is quite a long time, but it's quite a thorough explanation. Hopefully it wasn't too garbled, and hopefully it was helpful.